So I'm Levi Miller, and my partner is Nate Dixon. And for our project, we have made the Tetris video game. So the requirements for Tetris have the blocks need to fall at a regular interval. The blocks need to rotate so you can shift them into place. The rows need to clear when you fill up a whole row. And when the game is over, when the blocks reach the top, the game board needs to reset.
As you can see, the blocks are falling at a consistent rate, and the blocks will also rotate when we press the rotate button. Finally, when we clear a row, the row will be shifted down and the blocks will be removed from the screen. Finally, if we reach the top, then the game board will reset and the level will be reset to 0.
So there are 4 main hardware components to this project. First and most importantly being the STEM32 microcontroller, which drives the entire project and gives the power source. The project runs off a 3.3 power source coming from the board. The other 2 main components are the LED matrices and the shift registers. The main matrix is made up of 2 8x8 matrices, the schematic of which is shown here. The one matrix is arranged in columns and rows, which each intersection having an LED. When one column is brought to ground and one row is set to high 3.3, this LED will light up and none of the other ones will be lit. The game works by sequentially shifting in 1s and 0s into these spaces to light up the appropriate LEDs. Now, as you can see from the matrix over here, the rows and columns are kind of sporadically arranged, which is why there's a mess of wires on the board. Because it would be more convenient if all the rows were down here and all the columns were up there, but we had to move everything around to get them to light right. Also, we had to rotate this whole matrix by 90 degrees to get it to fit on the breadboard. So in this schematic, these rows became columns in our implementation, and the columns became the rows. So the polarity of everything was flipped in that sense. Now, if each LED were to be interfaced individually, we would need 128 I/O pins on the microcontroller, which we don't have. So to overcome that problem, we use shift registers, which effectively extends the number of pins available for us to use. One shift register will control all 8 columns, which are tied together, and the other 2 shift registers individually control each row. By shifting in serial data to the row shift registers, we can control each row individually. We'll shift 0s into here and 1 into the columns. So the columns will be brought high, the rows will be brought low. And that is how we control every LED on the matrix, only using just a handful of IOs from the microcontroller. We'll need 1 I/O to control the data, the serial data to the rows, 1 I/O to control serial data to the columns, and then the column uses a clock. It clocks in. Each bit is shifted into the register when the control clock goes high. As well over here, this also has a control clock that runs on the rising edge. When that clock goes high, a bit is shifted into these registers, and then there's an additional clock that latches the data out. So when that clock is brought high, data will appear onto the LED matrix. And the output clock is tied together between these 2 shift registers. So sending 0s here and 1s there, and then appropriately adjusting the clocks, we can control the LEDs on the matrix. However, it's not as simple as that. The LEDs also need to be multiplexed, or you're going to have the effect where unintentional LEDs are lit when you're adjusting the rows. So only 1 column is ever lit at once, and software will run through and turn 1 column on and 1 column off, preventing intersections here on the matrix and LEDs from lighting up unintentionally. As we can see over here on the board, there are only 5 pins used for interfacing this project because of the shift registers.
Okay, now I am going to explain to you how the software in this project works. So there are inputs from the joystick, and we also used inputs from the clock on the microchip. Because of this, we needed to include an interrupt for part of the project that displayed the screen, and we used the main function of the program to pull the joystick keys and keep track of the logic of the game. So this right here is the flowchart that explains our system tick interrupt, which displays the screen. How it works is it starts by getting a counter and it will count up. That way we can control the frame rate of the screen, how often it will update the screen. If the counter is full, it will move the block down. That way we can keep track of the time. That's how the blocks will move down by themselves automatically. And it works with a loop inside a loop. So the first loop will load the column data inside the shift register, which is 1 byte. And then the second one will load the corresponding bytes for the rows inside of the row vectors. We will display those columns, and then it will loop until it is finished doing the rows, and then it will loop after done all the columns. Now just going to show you an example of how it works. So here's our screen it's a 16 by 8-bit screen, and we want it to display this or something like this while the program is running. So what we'll do first is we will first display the first column, and only the 2 dots in the first column are lit up, so it will display those. Next, it will display the second column and those 3 bits. Next, the third column, and so on, displaying each and every column until all of the columns have been shown. And by doing this very quickly, by quickly turning on and off these lights, it gives the illusion that there is a full screen full of movement. Now the next part of the software handles what happens when we get input from the user. So this flowchart represents the main part of the program. So it will begin and it will pull the joystick pins. Because we pulled the pins, we needed to debounce them later. So first it will have a switch statement, which checks if the down button is pushed, and if the down button is pushed, then it will move to seeing if the blocks below the current block are filled. If they are not filled, it will move the block down. If they are filled, it will place the blocks and get a new shape or clear the row if the row is full. Or it will also reset if the game is done. If the left button is pushed, it will check to see if the left move is legal. If so, it will move the block left. If the right block is pushed, it will move the block right if it's legal. And if the up button is pushed, it will rotate the block if the rotation is legal. Finally, we will wait for the button to be unpushed. That's how we debounce the pin, so we'll only do one movement until it senses that the button has been unpushed, and then it will continuously loop for that throughout the entire program. And this concludes the software of our program.